In this problem, we're trying to determine whether the functions indicated by these three separate tables represent linear, quadratic, or none of the above. Well, linear will be such that the delta y is constant. Now, again, remember that's provided that the inputs are incrementally the same. So these go 2, 4, 6, 8, 10. These go 5, 10, 15, 20, 25. These go 4, 8, 12, 16, 20. So they're all equally spaced. For equally spaced inputs, if it's linear, the change in y should be constant. For quadratic, well, a quadratic is fully defined by the fact that the change in the rate of change is constant. So we can stop whenever we've come to one of these two things. Otherwise, if neither of these two are constant, then it would be none of the above. So in this case, well, it goes from -4 to -16, so the output drops by 12. -16 to -36, well, that's a drop of 20. -36 to -64, that's a drop of let's see, that would be 28, I believe. And this would be a drop of 36. Okay, so, well, these obviously aren't constant. These are the change in the y's. So next we would want to check the change in the y's. So this drops, this change in y goes from -12 to -20, so that's a drop of 8. This one goes from -20 to -28, so that's a drop of 8. And this goes from -28 to -36, so that's a drop of 8. So since the change in the change is constant, this represents a quadratic function by definition. This one, similarly, this goes 2, up by 2, up by 2, up by 2. Since this is the first difference, or the change in y, this represents a linear function. Now over here, we look at the change in the y, and we see that this goes 5, 10, 20, 40. Okay, so that's how much the inputs increase by, so that's obviously not linear. The outputs here, the rates of change go up by 5, and then by 10, and then by 20. So in this case, since neither of these two are constant, this represents neither of these two function types. Now there is a very specific name for this function type. It's actually an exponential, but we'll describe that in another chapter.